Good afternoon, all of you. So today I will give brief introduction about voltage regulation of transformers. So first of all, the definition of voltage regulation is it is change of secondary terminal voltage, change of secondary terminal voltage, change of secondary terminal voltage expressed as a percentage or per unit of secondary rated voltage, at a given power factor, load at a given power factor is reduced to zero with primary applied voltage held at constant. Primary applied voltage held at constant. E2 is the secondary induced EMF in transformer. V2 is the terminal voltage of the transformer, secondary rated terminal voltage. So E2 minus V2 by E2 is called voltage regulation. So voltage regulation is also called with VR. So voltage regulation, change of secondary terminal voltage, change E2 minus E2 minus V2 is called change of secondary terminal voltage when load at a given power factor is reduced to zero with primary applied voltage held at constant. So it is a ratio. Ratio means E2 minus V2 change by E2. Ratio of voltages. Ratio of difference of voltage by secondary voltage at no load. E2 is equal to no load secondary voltage. So this E2. V2 is called secondary terminal voltage at any load. So this depends upon this secondary voltage. This voltage regulation depends upon resistance of the transformer, resistance of the transformer, that is total resistance of the transformer, total reactance of the transformer, magnitude of the current, secondary current or load current, and the load power factor. 4 parameters. One is the resistance, R value, total distance of the transformer, total reactance of the transformer, and the secondary current of the transformer, I2, and the power factor of the transformer. And these 4 parameters, this voltage regulation depends: resistance, reactance, current, and power factor. So how the change occurs in transformer secondary terminal voltage, so that I will see. This is simple circuit. The simple circuit consisting of one voltage source, 200 volts voltage source, circuit having a resistance, load resistance. This is the load resistance, 38 ohms. So load, that means load. So this S is called switch. Having a cable resistance of 2 ohms. Having a cable resistance of 2 ohms. So 2 ohms is the cable resistance. 200 volts is the total supply voltage. 200 volts is total supply voltage. Here I will take only DC source, 200 volts. So this is the load resistance. So total resistance of the circuit equal to 38 ohms is the load resistance, 2 ohms is the cable resistance. So total resistance equal to 38 plus 2. That means 40 ohms. 40 ohms is the total resistance of the circuit. So 40 ohms is the total resistance of the circuit. So therefore, current delivered by when switch is closed, suppose when switch is closed, S is closed, total resistance equal to 40 ohms. So I equal to current delivered by this source, I equal to 200, I equal V by R. So I equal V, P value 200, P value 200, voltage by resistance value 40. Total resistance equal to 40. So 0, 0, 5. So that means 5 amperes current. So that means current flows to this delivered with this source equal to 5 amperes. 5 amperes current. So 5 amperes current passes through this loop. This loop carries 5 amperes of current. So that means So when current passes through this 2 ohms resistance, voltage drop across this resistance, equal to IR, V equal to IR, So I value 5 amperes, ohms, 5 into 10 volts. So this is equal to voltage drop across resistance equal to 10 ohms. So then VR voltage drop across resistance equal to 10 volts. That means 10 voltage drop occurs, 10 volts drop occurs across this resistance. Total source voltage equal to 200 volts. So 200 minus 10. So remaining voltage appears across this resistance. Remaining voltage appears across this load. Okay. So that means voltage drop across this load equal to equal to 190 volts. 190. Okay, 190 volts. So total source voltage 200 volts. Because of resistance drop across the resistor 10 volts. So some voltage is reduced across the load. So voltage drop across this load equal to 190 volts only, not 200 volts. So that is because of resistance drop. If you add some reactance in series with that resistance, some more voltage will drop across that combination of resistance and reactance. So that means source voltage does not appear across the terminals. Depends upon resistance and resistance parameter value and current through that resistance value. So this voltage 190 volts is not constant. If load resistance changes from 38 to 48 or 38 to 36 or 30 volts, 30 ohms, if load resistance changes, current through this resistance changes. Current through that resistance changes means voltage drop across that resistance value changes. Voltage drop across the resistance value changes means voltage appears across this RL value changes. So that means this 190 volts is not constant. That value changes from some maximum value to some minimum value. That depends upon load resistance value. This load resistance changes means current changes. Current changes means voltage across this resistance changes. So in this manner, terminal voltage of the load always changes, or secondary terminal voltage of the transformer always changes. So that I will explain. Suppose we have equivalent circuit in our transformer. So transformer equivalent circuit is so I will try equivalent circuit here. Shunt branch, equivalent circuit of the transformer, shunt branch. So total resistance of the transformer, total reactance of the transformer. So this is the equivalent circuit of the transformer. Okay. So this is R equivalent. This is X equivalent transformer. So this equivalent circuit is, suppose this equivalent circuit is referred to secondary. Equivalent circuit referred to secondary. Secondary induced EMF. Secondary induced V2. So here V2. Okay. So equivalent reactance referred to secondary. Equivalent resistance referred to secondary. So this is a shunt branch. R equivalent refer to secondary, X equivalent refer to secondary. So this is the induced EMF on secondary. So terminal voltage of the transformer. This is the terminal voltage of the transformer. So if you neglect this shunt branch, the shunt branch current is very small. So shunt branch current is very small means if you neglect this one, approximate equivalent circuit. So this is the approximate equivalent circuit of the transformer. So if we neglect this shunt branch, this is the approximate equivalent circuit of the transformer. Okay. So this is the approximate equivalent circuit of the transformer referred to secondary side. R equivalent total resistance of the transformer referred to secondary. R equivalent of 2. So primary resistance to secondary resistance. X equivalent to 2. X equivalent to 2. Equivalent is total reactance referred to secondary. So this is the resistance to secondary total resistance. So total resistance means having primary plus secondary. Total reactance also consisting of primary reactance plus secondary reactance. So this is the equivalent circuit of the transformer referred to secondary when we neglect the shunt branch. So when load is connected here, transformer load is connected here. So we connect load across this terminals of the transformer. So this is the RL value. So load is connected here. So when we so this is the load resistance. So this load resistance is not constant. This is a variable resistance. So when we vary the load, current of the circuit changes. Secondary current of the transformer changes. I2. So this I2 value depends upon RL value. Load resistance value. Load resistance varies. I2 value varies. So the voltage regulation of the transformer depends equivalent resistance of the transformer, equivalent reactance of the transformer, and load current. Load current depends upon total load and power factor of the load and power factor of the load. 3 parameters: resistance, reactance, current, and power factor, cos theta, and power factor. So in this way, if we vary the load, current varies. Current varies means resistance drop across this resistance, reactance varies. Voltage drop across resistance and reactance varies. So voltage of the secondary terminal voltage of the transformer always changes. That depends upon resistance, reactance, and magnitude of the load current and the load power factor. So the voltage regulation of the transformer can be obtained from its approximate equivalent circuit referred to secondary. The approximate equivalent reactance, resistance, secondary induced EMF voltage, terminal voltage. So this is the approximate equivalent circuit. Secondary current I2. Here we neglect the shunt branch. Total reactance, total resistance, and secondary voltage. First of all, we draw the approximate equation for this one. Equation for this approximate equivalent circuit. So resistance, reactance. So this is the approximate equivalent circuit. E2 value, E2 value, and X2 value, I2 value. So here E2 is the source. So source voltage equal to E2 equal to source voltage. So source voltage equal to So resistance drop I2 R2 I2 R2 plus reactance drop I2 X2 plus V2 plus V2. Here J means reactance component, the nickel component. So induced limit V2 equal to resistance drop plus reactance drop plus V2. So this R2 plus JX2 means impedance. R2 plus JX2 is called impedance. So I2 Z2 plus V2. I2 Z2 plus V2. So this can be written as so E2 equal to V2 plus I2 Z2. Z2 means resistance plus reactance. Here Z2 equal to R2 plus JX2. Z2 equal to R2 plus JX2. So this is a vector sum. This is a vector sum because AC circuit. So E2 equal to V2 plus I2 Z2. So for this is the equation for second D. We draw the phasor diagram for this one. So first of all, we take V2 as a reference. At lagging power factor, current lags the voltage. Current lags the voltage. So this I2 R2 is in parallel with I2. So I2 R2. Reactance component is perpendicular. So that is I2 X2. This is I2 Z2. So this is the E2 value. So E2 equal to V2 plus I2 Z2. So E2 equal to V2 plus I2 Z2. So this is phasor diagram. So this is the phasor diagram at the lagging power factor. Phasor diagram at the lagging power factor. So here V2 is taken as reference. V2 lagging power factor means current lags. So this is the current value I2. I2 R2 is parallel. I2 X2 is perpendicular. I2 Z2 value this one. This is the E2 value. So E2 equal to total impedance drop plus V2. So this is the phasor diagram of the transformer at the lagging power factor. See, for calculating the voltage regulation, draw an arc of OD meeting extension of the line at F. So this is the arc value. Here we draw the arc value from O. So total E2 value equal to OA, AB plus BC. So OA value means this one. OA value. So this is the OA value. OA up to here. And I2 R2 cos theta 2. So AB dash value this one up to here. And further this total value. Total value. So therefore E2 equal to OA plus AB plus BC. So OA value is V2. AB value I2 R equivalent of cos theta 2. BC value I2 X equivalent of sin theta. One is the horizontal component, second one is the reactance in the perpendicular component. Horizontal component plus perpendicular component. So for calculating the voltage regulation, draw an arc and draw therefore V2, I2 R2, I2 X2. So this is approximately equal, not exactly equal, it is approximately equal. So E2 minus V2, if V2 is transferred to the right side, E2 minus V2 equal to this one. Okay, so voltage regulation definition. Voltage regulation equal to change of voltage by E2. this equation is substituted here. This equation is substituted here. So voltage regulation equal to E2 minus V2 by E2. So therefore voltage regulation equal to I2 R equivalent to cos theta to this component by E2 value separated. I2 x equivalent of 2 by E2 into sin theta. Okay, so this term is called, we call per unit resistance. This term is called per unit reactance. Resistance is based per unit resistance. Reactance is based per unit reactance. So we replace this one with sigma R. Replace this one with sigma X. Sigma R and sigma X. So this is a lagging power factor. This is a lagging power factor. So this is the formula for calculating the voltage regulation at lagging power factor, because we take current lagging here. We take current lagging here. Okay, next case 2, this is the leading power factor. Leading power factor. First case lagging power factor. Okay. Case 1, this one is for the lagging power factor. So next for leading power factor. Current leads the voltage, terminal voltage. See, current leads. This current leads the voltage. So first draw the voltage, the phasor diagram at leading power factor. And same way, write down the equation for E2. So this is the V2 value, current leads V2, I2 R2, I2 X2. This is I2 R2, this is I2 X2, this is I2 Z2. So this is the E2 value. So this E2 equal to V2 plus resistance component, V2 value this one. So this is the V2 value. Okay, resistance component, particular component, active component, I2 R2 cos theta 2. So reactance component, this one. This is a reactance component, this one. This is one. So this is the E2 equal to V2 I2 R2 minus value, minus subtracted. Because we want E2 value, this want E2 value, minus I2 X2 sin theta. Same formula for voltage regulation, this is the formula for voltage regulation. We should substitute this equation in this one. So we get just minus here. In last case, plus, here only minus. Same with this value we call sigma X. This value we call sigma X. This was sigma R, sigma X, just minus. So what means voltage regulation sigma R cos theta 2 minus sigma X sin theta. For lagging power factor, sigma R cos theta 2 plus sigma X sin theta. So that is the leading for lagging power factor and for leading power. So therefore, for in general voltage regulation we write it as voltage regulation sigma R cos theta 2 plus or minus. Plus is for lagging power factor, plus is for lagging power factor, minus is for leading power. So here plus for lagging power factor, minus for leading power factor. So this is the general voltage regulation formula and transformer. Where sigma R means I2 R2 by E2 value. Sigma R means I2 R2. This I2 R equivalent of 2 by E2 value. Sigma X I2 X equivalent of 2 by E2 value. Okay. So condition for zero voltage. What is the condition for zero voltage? So condition for zero voltage. So this is the voltage regulatory formula. The voltage regulation is varied with load power factor. The load power factor is varied with connection values. Load current, keeping load current and keeping the EM, and the voltage regulation, zero voltage will be zero voltage that is equivalent to 0. Voltage regulation is not of theta zero. So this is equal to calculation. From this calculation, theta to equal to sigma R by sigma X. To write the sigma R by sigma X equal to in terms of resistance reactance. So this is the tan theta value. So if this is the tan theta value, this is the cos theta value. So cos theta equal to X equivalent of 2 by Z equivalent of. This is very, very important. So this power factor, this is nothing but a power factor. theta. Voltage regulation will be 0. In a transformer, voltage regulation will be 0 when cos theta equal to reactance component X. Reactance by impedance. Reactance by impedance. Just simply put this equation into 0. Voltage regulation equal to 0. So this is the condition for voltage, 0 voltage regulation. Condition for 0 voltage regulation. Very, very important. Condition for 0 voltage regulation. Just simply equal to 0. Just simply equal to 0. Simply put it 0. This is the condition of 0 voltage. Zero voltage regulation. So that is the condition for 0 voltage regulation. Just simply equate to 0 and calculating. This is the tan theta value. Because tan theta to the cos theta equal to sigma r by sigma x. Substitute sigma r value and sigma x value, and then we get tan theta value. This is equal to, then tan theta equal to this means cos theta equal to this value. Okay. So that is the formula for 0 voltage regulation. Negative sign value of theta to indicates voltage regulation will be 0 for leading power. Why negative value indicates means for leading power factor 0 voltage regulation occurs. At what power factor 0 voltage regulation occurs means at the leading power factor 0 voltage regulation occurs in transformer. Next condition for 0 voltage. Last case condition for 0 voltage regulation. The condition for maximum voltage. The condition for maximum voltage regulation is obtained by differentiating the voltage equation. So then this is the voltage regulation equation. The voltage regulation equation. So differentiate this equation with respect to theta.
Sir, develop supervise.
By keeping E2 and I2 constant. By keeping I2 and E2
Hello.
constant, differentiate the voltage regulation equation with respect to theta. Because voltage regulation varies.
Sir, your voice is not audible.
Not perfect. So that means theta. Differentiate to
Supervise.
sin theta.
Hello.
Become sin theta. Sin theta to become
Hello.
differentiate. Hello.
Hello.
This
Sir.
calculation. Sigma x cos theta, sigma r sin theta times tan theta equal to x equivalent to r equivalent. Tan theta equal to this one. This is the cos theta value. At this point, the voltage regulation will be maximum. When this point is positive. So it will be
Sir, my voice double impression.
maximum voltage leading power. At this power factor, voltage regulation will be maximum. This is the condition for maximum voltage regulation. What is the value of maximum voltage regulation? Substitute the condition in this equation. So maximum voltage regulation occurs equal to R equivalent of 2 by Z equivalent of 2 sigma x equivalent of 2 by Z equivalent of 2. After calculation, sigma r value I2 R equivalent of 2 by E2. So simply substitute sigma x value. Calculation. So this is the value. This is the value of maximum voltage regulation. Maximum voltage regulation equal to I2 Z equivalent of 2 by E2. So that is also called per unit impedance. It is also called per unit impedance. This value is called per unit resistance. This value sigma R is called per unit resistance. Sigma X is called per unit reactance. Sigma Z is called per unit impedance. Per unit. This value is called per unit impedance. So this is the condition for maximum voltage regulation and value of maximum voltage regulation. Okay. This is the condition. This is the condition for maximum voltage regulation. Cos theta 2 equal to R2 by X2. Remember here R2 by X2 in last case that is X equivalent to by Z. For zero voltage regulation. For zero voltage regulation, here X2 equivalent reactance to impedance for zero voltage regulation. For maximum voltage regulation, R equivalent to by Z equivalent to 2. So voltage regulation means change of secondary terminal voltage from no load to full load. Voltage regulation means change of secondary terminal voltage from no load to full load. Expressed as a rated no load voltage. It means E2 minus V2 by E2 minus V2 by so voltage regulation is different as the second change of terminal voltage E2 minus V2 by E2 value. It depends upon resistance, equivalent resistance, equivalent reactance, total load current or secondary current, and power factor of the load. 4 parameters: resistance, reactance, current, and power factor. So this is the voltage regulation. Calculating voltage regulation in equivalent circuit, we neglect the standard branch. If you neglect the okay. If you have any doubts, any doubts? So voltage regulation means change of secondary terminal voltage from no load to full load. So at no load, secondary terminal voltage E2 and V2 both are equal because current equal to 0. No load means current equal to 0, I2 equal to 0, I2 equal to 0 means both are equal. Both are equal. E2 equal to V2. So at no load. When load is connected, I2 will exist. I2 will exist means some voltage drop across the impedance. Because of that voltage drop, terminal voltage of the transformer changes. So in some cases it increases, in some cases it decreases depending upon the power factor of the load. So V2 changes. The change is called regulation. Change of secondary terminal voltage from no load to full load is called voltage regulation of the transformer. Okay. So this is the formula for calculating the voltage regulation. Formula for calculating the voltage regulation. So voltage regulation equal to change of secondary terminal voltage to minus V2 by E2. It depends upon resistance, reactance, current, and power factor. Okay. So this is voltage regulation for lagging power factor. Formula for voltage regulation for lagging power factor. So this is simply sigma r cos theta 2 plus sigma x sin theta 2. Sigma r means per unit resistance, sigma x means per unit reactance. So voltage regulation. So there is a voltage regulation. Voltage regulation equal to sigma r cos theta 2 plus sigma x sin theta 2. So this is the voltage regulation for lagging power factor. For leading power factor, same calculation. Sigma r cos theta 2 minus sigma x sin theta 2. Sigma r cos theta 2 minus sigma x sin theta 2 for leading power factor. Just the same sign changes. Okay. Plus for lagging, minus for leading. Next condition for zero voltage regulation, condition for maximum voltage. For zero voltage regulation condition, cos theta equal to x equivalent of 2 by z equivalent of 2. For maximum voltage regulation, cos theta equal to r equivalent of 2 by z equivalent of 2. For zero voltage regulation, reactance component by impedance component. For maximum voltage regulation, resistance component by impedance component. For these are the conditions. Okay. So maximum voltage regulation value called per unit impedance value. Just simply very per unit impedance value. Okay. So with this today I will conclude the class. If you have any doubts? Okay, thank you.